Okay, so we're back for more fun with KSP. I left off saying that we were going to look at a problem that involved the common ion effect. So let's do that. So let's look at this problem. Let's say that we're looking for what is the solubility of lead-2 iodide in the presence, so in in solution with, that's not spelled right, of 0.1 molar potassium, my God, lead-2 nitrate. Okay, so the first thing I'm going to do is I'm going to write the dissociation of the salts. So that's always the first step. So I have lead-2 iodide, which is going to go to a lead-2 ion and 2 iodine ions. And then I also have this lead-2 nitrate, which is going to go to a lead ion again, and 2 nitrate ions. So you should see here that there is a common ion, and the common ion is in fact this lead-2. This is our common ion. It's worth noting that common ions decrease solubility. So the solubility of lead-2 iodide on its own in comparison to the solubility of lead-2 iodide in the presence of a common ion is different. Okay, so in the presence of the common ion, there is going to be a decrease in solubility. So what I'm going to do now is I'm going to rewrite the dissociation of the lead-2 iodide, since that's what I'm looking for in terms of the molar solubility, and I'm going to ice this. So when I make my ice table, same as always, we don't care about the initial. Now, initially, I have to be careful here. How much do I have of the lead ion? Because I'm in the presence of 0.1 molar lead-2 nitrate, I have 0.1 molar lead to begin with. So I'm starting out with 0.1 molar of lead, and I don't have any iodine. I'm going to gain X, and I'm going to gain also 2X of the iodide. So at equilibrium, I have 0.11 plus X of the lead and 2X of the iodine. So I'm running out of room here. Let's see, I'll try to fit some stuff here. So the KSP is going to be equal to the concentration of the lead times the concentration of the iodide squared. So when I put this together, and I needed to give you the KSP of the lead-2 iodide, so that's my bad. So the KSP is equal to 1.4 times 10 to the minus 8th. So given that KSP, I can now continue making this expression. So I say the KSP, 1.4 times 10 to the minus 8th, is equal to 0.11 plus X times 2X for the iodide squared. So the deal with this X is that the X is going to be relatively small compared to 0.1, meaning 0.11 plus X is basically 0.1. It's a very small amount, so it's negligible, so we can actually get rid of the X. So that leaves us with 0.11 times 2X squared. Now, we talked about how to deal with this 2X squared before, so I'm going to square the 2, that squares the X, so you end up getting 4X squared. So I'm going to do 0.1 times 4X squared, and then I'm going to divide that by the 1.4 times 10 to the minus 8th. So if I just make this a little bit cleaner now, I have the 1.4 times 10 to the minus 8th, so I would divide this by 0.1 times 4, So I'm dividing by 0.1 times 4, and I would take the square root of that, and that would then give me the x. So the x turns out to be 1.9 times 10 to the minus 4th, and remember that's our molar solubility. So that would be our answer here. Okay, so that's a common ion effect, so you got to always look out for that. Next, we're going to talk about other factors that can affect the solubility, such as pH. So let's look at the following problem. Let's say that I have a saturated solution of, I don't know, I already used magnesium, barium hydroxide, and it has a pH, so a saturated barium hydroxide has a pH equal to 12.4. And I want to know what is the KSP for barium hydroxide. So this is a bit bizarre. I bet if you are not familiar with this, this may be confusing. What do we do? So as always, I'm going to start the same way. You know, I'm big on procedure, so we're going to start the same way. I have barium hydroxide, which dissociates into barium ions, or a barium ion, and 2 hydroxide ions. Now, immediately, my attention is drawn to this hydroxide ion, because I need to find, you know, a concentration of the hydroxide ion to plug into my KSP expression. And since I know the ratio of hydroxide ion is to barium is 2 to 1, half of the hydroxide ion concentration would be equal to the barium concentration. And that I can get from the pH, the hydroxide ion concentration. So I kind of have an idea of what we're going to do here. But as always, the first thing I'll do is make my KSP expression. So I'm going to make a nice table. This is negligible, or not negligible, non-existent. So I start off with 0 of the undissociated product. I'm going to gain x here, gain 2x here for the hydroxide. So same thing, make the KSP expression. So KSP will be equal to the concentration of the barium times the concentration of the hydroxide squared. Okay. So now the question becomes, what goes in here? So let's do some little math over here off to the side. So I have a solution that, I have a solution that has a pH equal to 12.4. In turn, I know the pOH would be equal to 14 minus 12.4. So the pOH equals, 1.6. Then I know the pOH is equal to the negative log of the OH concentration. So 10 to the negative 1.6 is going to equal the OH. So the OH concentration turns out to be 0.0251 molar. So I know that's going to go in here for the hydroxide ion concentration. Now the question becomes, what is the barium concentration? And like I said, since the ratio of hydroxide to barium is 2 to 1, the barium ion concentration would just be half of that of the hydroxide ion concentration. So it's half, if I wanted to write it in terms of the hydroxide ion concentration, the barium is half of the hydroxide ion concentration. So it's going to be 0.0251 divided by 2, so that would be 0.0126 molar. So now we can find the KSP. We just multiply these two numbers together, and we find the KSP to be 7.94 times 10 to the minus 6. So fairly insoluble, pretty small, or on the smaller side of KSPs. So we wouldn't expect this to be super soluble, but that is how pH can affect solubility, or rather how you can find solubility from pH. One last thing to talk about, and I'm sure you guys will be excited about this one, but Q is back for revenge. So we're going to discuss precipitation, reaction, quotients. So, what incarnation does that mean? Well, the question is, how can we determine, or how can we know, if precipitation occurs or not? Meaning, I have a solution, I mix them together, and I want to know if I'm going to form a precipitate or not. And we're being more specific here. Given values, how can we know precipitation will occur? Not just whether we're going to form an insoluble product or not. So we're going to relate this to Q and KSP. So we're going to relate the reaction quotient Q, remember that from equilibrium. What am I doing? Relate Q to KSP. So we're going to have a same kind of Q greater than KSP business again. So if Q is greater than KSP, we have what's called an oversaturated solution, meaning there is a high concentration of ions in the solution, and because it's oversaturated, it's going to precipitate. So precipitation will occur. So when Q is greater than KSP, we have an oversaturated solution, therefore precipitation occurs. Now what if Q is less than KSP? Well, in that case, you have an undersaturated solution. It doesn't have enough ions in it. And because of that, you have no precipitation. Now, what if Q is equal to KSP? Well, in that case, you're at equilibrium. Just trying to make a cool at sign, but it didn't work. You're at equilibrium. However, the solution is a saturated solution. However, no precipitate will occur. What does a saturated solution? Did I spell it right? Precipitate, yeah. What does a saturated solution mean? Well, it's just at its maximum solubility. So you can think of oversaturated, undersaturated, and saturated as the following. If I have a cup of salt water and I keep adding salt until it all dissolves, when it's all dissolved, that means that I have a saturated solution. I've dissolved the maximum amount of sodium chloride that would dissolve in this solution. If I keep adding sodium chloride, it's not going to dissolve anymore because I exceeded the solubility. So it's not going to dissolve anymore, and you're just going to end up with extra sodium chloride floating around that's not dissolved. That's oversaturated. Undersaturated means I haven't reached that maximum solubility yet, so I'm going to keep dissolving and, I could keep dissolving more sodium chloride. However, I'm not. So it's undersaturated. It hasn't reached that saturated point yet. So why is this useful? Why do we care about any of this? Well, we care because we can determine precipitation given KSP and given Q. We can determine if precipitation will occur. So this is just more of an application of KSP. So let me show you an example of this. So let's say that if 10 milliliters of 2.0 times 10 to the minus third molar chromium 3 nitrate, chromium 3 nitrate, is added to 10 mils of a NaOH solution with a pH equal to 10, will a precipitate form. And the KSP is equal to 6.7 times 10 to the minus 31st. So it's ridiculously small. It's barely barely is an understatement. It really doesn't dissolve. But this may seem like intimidating. There's a lot going on here. So the first thing I'm going to do is write the double displacement reaction that occurs between chromium 3 nitrate and sodium hydroxide. So I have chromium 3 nitrate. Chromium 3 nitrate, and this is indeed soluble. Hold on, this is not. This is aqueous. I'm mixing that with sodium hydroxide. And this is going to be an equilibrium reaction. And remember, it's just a double displacement. So double displacement means we switch partners. So the sodium will go with the nitrate. The chromium will go with the hydroxide. So you end up getting chromium 3 hydroxide. Now this is insoluble. This is a solid. And you get sodium hydroxide. Sodium nitrate, which is aqueous. So remember, solubility rules come into play here because you got to know that's insoluble. One other thing we have to deal with is this isn't balanced. I have 1 nitrate here and 3 over there. So I'm just going to put a 3 in front of there. That messes up the sodium over here, so I'll put a 3 there. And that ended up fixing our hydroxide dilemma, so we're good. So now what I'm going to do is I'm going to dissociate the precipitate, or the solid. So I'm just going to write an equation that represents the dissociation of the chromium 3 hydroxide, or rather the formation of it. Either one is fine, but I'm going to write that chromium 3 ions and hydroxide ions, or actually 3 hydroxide ions to be exact, will form chromium 3 hydroxide. So what I want to do now is I want to determine the Q values for chromium. So I'm going to determine the Q value of each, the chromium and the hydroxide ion. Why? Well, if I find the reaction quotient, I can compare that to the given KSP, and we know our answer, whether it will precipitate will form or not. So how do I go about this? Well, I need to know, remember Q is a measure of products over reactants. However, in this case, we don't need to kind of think of it in that manner. We're just going to do it in the following way. So let's say that I'm looking at the Q of the chromium. What do I know? Well, I know that I have 0.0100 liters of the chromium. Remember, it's 10 milliliters, so that's 0.01 liters. Has a concentration of 2.0 times 10 to the minus third. And I know the total volume is 0.0200 liters. So what I'm going to do is I'm going to find the concentration of both the chromium and the hydroxide, and from there I can get the Q value. So it's a two-step process. I can't go right to the Q. I have to determine the concentration first. Remember, this is the total volume. It's 20 mils, so it turns out to be 0.02 liters. So this should be 1.0 times 10 to the minus third molar. So that's the concentration of the chromium. Now I need to find the concentration of the hydroxide ion. Problem is this is not given to us. So we're going to have to be a little creative. I know the pH, so from there I can find the hydroxide ion concentration. So I'm not going to write the whole thing out. I'll just kind of make a little thing over here and say the pH is equal to 10. The pOH is then equal to 4. So you can net the hydroxide ion concentration, and that should equal 1.0 times 10 to the minus fourth molar. So I go back to my hydroxide ion concentration calculation. I have 10 milliliters or 0.01 liters of the sodium hydroxide, so that's where the hydroxide ion will come from. We just determined the concentration to be 1.0 times 10 to the minus fourth, and the total volume is 0.02 liters. So we get 5.0 times 10 to the minus fifth molar hydroxide ion. Now we're cooking. I can find my Q value. Remember, Q is just products over reactants. But like I said, we don't have a concentration of this chromium hydroxide initially, so we don't have, similar to the KSP, we don't have to do a reactant calculation. So it can just be the chromium times the hydroxide ion concentration for our Q, because we don't need to worry about the concentration of the chromium hydroxide, chromium 3 hydroxide itself. So I'll plug in these numbers we just found. I found the chromium to be 1.0 times 10 to the minus third, the hydroxide to be 5.0 times 10 to the minus fifth. And when I cube this, remember this should be cubed because we have 3 hydroxide ions. Whoops, I missed it over there. So 3 hydroxide ions, cubing that, we will find this to be 1.3 times 10 to the minus 16th. So this is what Q is equal to, and let's remind ourselves that the KSP that was given to us is equal to 6.7 times 10 to the minus 31st. So what is the relationship between Q and KSP? Well, Q is much bigger than KSP, and when that is the case, we have an oversaturated solution. Saturated solution. So a precipitate forms. So yes, a precipitate will form. So a little bit involved here. These are slightly tricky, but once again, not really terrible in the grand scheme of things, but we will do some practice with this. Okay, see you.